Hi, my name is Michael Bradkey. My supervisors are Kimball Marriott and Samuel Randers. Throughout this presentation, I'll be discussing my thesis, zooming and panning on refreshable tactile displays to support accessible data visualization. People who are blind or have low vision share the same data-related needs as sighted individuals for problem-solving, reducing uncertainty, and facilitating personal growth. With 453,000 blind or low vision people in Australia, with an expected 564 by 2030, access to data visualization is crucial in today's data-driven society, impacting education, work, lifestyle, and health. Common tools for addressing blind or low vision access to data visualizations include sonification, which uses sound to convey data, tactile graphics, otherwise known as raised line drawings, which convey information through touch, and refreshable tactile displays, or RTDs, which use actuating pins to tactually present graphics and visualizations. Crucially, RTDs remove the cost and labor associated with individual tactile graphic production, as the device can refresh to display multiple graphics within seconds. While RTDs offer significant benefits for blind or low vision data accessibility, their low resolution limits the display of rich information without graphical manipulation. To address this, exploring zooming and panning techniques is essential. Although previous research has touched on these methods, a gap still remains in how to best implement these interactions for blind or low vision users. This research aims to address the following questions. How do we best support zooming and panning on an RTD for blind or low vision users? As well as, how do we maintain sense of location and minimize disorientation when performing zooming or panning on an RTD? Co-design is a user-centered research method that involves engaging consumers and stakeholders throughout the design process to address their needs and preferences. This study used the co-design methodology with two independent co-designers to develop input interactions for zooming and panning, along with system outputs to help maintain location and awareness while minimizing disorientation. We developed 5 distinct interaction types for zooming and panning. Most notably, for zooming, we combine touch and voice commands, such as touching a location and saying zoom in where I'm touching. For panning, we enabled swipe gestures similar to those used on smartphones and tablets. We developed 2 system outputs, being scroll bars, using single pixel width bars to show a position and magnification, which shrink when zooming in and enlarge when zooming out, and a mini-map, a 6x4 pin grid with a dynamic bounding box that adjusts in size based on the zoom level. We conducted a user study to evaluate the effectiveness of the zooming and panning interactions and how scroll bars and mini-maps help reduce disorientation. Using a Wizard of Oz method, participants interacted with the RTD, unaware that a wizard was controlling the interface to simulate complex functionality, without full implementation of a touch-sensing autonomous conversational interface. A graphical user interface was developed using the Graffiti API and Motion Leap 2 controller to allow the wizard to fulfill participants' interactions during the study. In this study, participants engaged with an isorhythmic map of Australia, illustrating predicted temperature variations between the years of 2020 and 2050. They completed 3 tasks using their chosen zooming and panning methods on the RTD, followed by ranking each interaction. Participants then explored and ranked the effectiveness of the scroll bars and minimap. These rankings based on how well they aided their sense of location and awareness while minimizing disorientation. Results concluded participants favored a combination of touch and voice for zooming and gestures for panning, with the highest ranking system output being scroll bars. Thematic analysis revealed 7 key themes among participants, most notably enhanced understanding through zooming, with participants expressing that the ability to zoom enhanced their understanding of the data visualization. In addition to maintaining location and independence, a number of participants described how maintaining a point of contact with the RTD through touch when zooming, for example touch and voice, improved their ability to maintain their sense of location, as well as disorientation, with participants finding regardless of how well designed interactions are, there is always some form of contact loss associated when the screen is refreshed. Participants' overall experience when interacting with the RTD, leveraging various zooming and panning methods to explore the data visualization, was very positive, expressing how both zooming and panning are integral in successfully exploring data visualizations on the RTD, particularly in overcoming the low resolution constraints dictating how much rich information can be displayed on an RTD. We speculate the fondness for touch and voice zooming was due to the greater control that it gave participants, particularly as a result of the touch aspect of the interaction. while we suspect gestures ranked highest due to participants' prior experience with technology influencing their interactions. While some participants appreciated the integration of scroll bars for improved awareness of location and magnification, they were less enthusiastic about the minimap, possibly due to being an inherently visual concept. Based on our observations and evaluation results, we developed 3 design recommendations. These included intuitive interactions leveraging touch, whereby zooming should be primarily supported by the inclusion of the touch and voice interaction. As findings suggested, having a point of contact can lead to an improved sense of location. We recommend that RTDs also support user-defined customization, allowing users to customize the behaviors and mappings of different interactions as participants desire to dictate the direction the visualization moved when performing a pan using gestures. While we recommend RTDs integrate contextual scroll bars for enhanced navigation, as participants express the benefit of scroll bars in maintaining location and independence while minimizing disorientation when interacting via a zoom or a pan. Firstly, this study focused purely on the presentation of temperature change data. Therefore, visualizations containing more complex data representations should be investigated to see if interaction preferences differ with ranging complexity of information. Additionally, the majority of participants were totally blind. Therefore, we are interested in recruiting participants with varying degrees of blindness, as their perspectives may influence interaction preferences. Lastly, participants were of similar age. Future research involving a greater age range of participants, particularly younger age individuals, may see differences in interaction preferences. Ultimately, we believe that the findings of this study serve as a stable basis for the design of future RTD devices that can enable independent and purposeful data exploration and analysis.